Okay, now let us talk about the second part of molecular kinetic energy and internal energy. Okay, previously you learned that for each degree of freedom, in one molecule, in one degree of freedom, okay, remember, 1 degree freedom, it only store a kinetic energy of half kT. For 1 degree of freedom in one molecule, it only store a kinetic energy of only half kT. That's the smallest building block, we can say, smallest building block, of energy. Okay. Now, let's say if the question asks for the average mean kinetic energy of one gas molecule, actually the word, let me highlight this one. The word mean, already means that one molecule. Okay. Sorry. Already asked for one molecule. Okay. Now, if the question asks for average or mean, it can be average or mean, same meaning. Average or mean kinetic energy of one gas molecule. Okay, we start with half kT. What is half kT again? Half kT is the energy for 1 degree freedom in 1 degree freedom, isn't it? But for one gas molecule, it has many degree of freedom. Depend on what type of gas. Either it's monoatomic, or diatomic, or polyatomic. If monoatomic, it has 3 degree freedom. Yes, diatomic is 5 degree freedom. If polyatomic, it has 6 degree of freedom. So, in one gas molecule, it has many degree of freedom. Depend on what type of molecule. Okay, so in one gas molecule, it already has, can say it has F, it has F degree of freedom. Okay, it already has F degree of freedom for one gas molecule. So energy for 1 degree freedom is half kT. So in one gas molecule, it has F degree of freedom. If it is a monoatomic, it has 3 degree freedom. It is a diatomic, it has 5 degree freedom. It is a polyatomic, it has 6 degree freedom. So half kT for one gas molecule, we just take half kT multiply F. F can be 3 if mono, can be 5 if diatomic, it can be 6 if polyatomic. Okay, so in general, just multiply F. So multiply and then we get F over 2 kT. Multiply to here, we get F over 2 kT. So the kinetic energy for one particle, for one gas molecule, is F over 2 kT. Okay, F over 2 kT. That's it. For one gas molecule, half kT. You always start with half kT. You see that? Maybe I should highlight this one. I always start with, all the question, I always start with half kT, half kT, half kT. And then the last one also, I start with half kT. You see that? I already said this half kT is the building block. The building block for all the energy. Okay, so for one gas molecule, it has F degree of freedom. So just multiply F, you get F over 2 kT. Now, if the question asks for average translational, is specially mentioned. If let's say the question specially mentioned, I only want the translational kinetic energy for one. Maybe this is a polyatomic. Maybe let's say this is a polyatomic gas molecule. So polyatomic, we know that it has 6 degree of freedom, isn't it? Yes, 6 degree of freedom. But if the question explicitly just want the translational kinetic energy, so the F you don't put 6. The F you don't put 6, although it's polyatomic. You don't put 6. The F you should put only 3. Because the question only want the translational part. The translational part of kinetic energy. So the F automatically you put 3. Don't put 6. If you ask for, if this is a diatomic molecule, also F don't put 5. I know diatomic has 5 degree freedom. Don't put 5. Because the question asks for translational kinetic energy only. So the F you should put also 3. Okay? So 3 times half kT, you get 3 over 2 kT. That's the translational kinetic energy for one polyatomic gas molecule. Okay? There is only one gas molecule. Now, what if I have 1 mole of gas? More than one gas molecule. I have 1 mole of gas. How many gas molecule in 1 mole of gas? Whoa, that's a lot. 1 mole of gas has, remember the number? The number is 6.02 exponent 23 of molecule. Okay? So what is the total? What is the total kinetic energy for 1 mole of gas? What's the total kinetic energy for 1 mole of gas? Yeah? 1 mole of gas has this amount of molecules, or we can say Avogadro constant, Na molecules. 1 mole of gas has Na molecules. So we start with the half kT for 1 degree freedom. Energy for 1 degree freedom. Energy for 1 degree freedom is half kT times F degree freedom, because for one gas molecule, it has F degree freedom. So you must multiply by F degree freedom. So you must see this is a monoatomic or diatomic or polyatomic. Then the F you use accordingly, 356. So multiply F, multiply by, because we have we not just only have one gas molecule, we have 1 mole of gas molecule, which is 1 mole is how many molecule? Na molecules, Avogadro constant molecules. So we need to multiply the Avogadro constant, because 1 mole has Na molecules. So multiply by this molecule. So the total kinetic energy for 1 mole of gas, you need to multiply by the Avogadro constant. So which you will get this one. You still remember? R equal to Kna, the formula, R equal to Kna. The R here, see this one? The K here, the K here and the Na here. See the K here and the Na here. K multiply Na, you get R. So you get R. Yeah, the K over here. Sorry, something wrong. Yeah. The K here and the Na here multiply, you get R here. Okay, get R here. So the formula for total kinetic energy for 1 mole of gas, you use F over 2 RT. So remember, if only one gas molecule, it is use K. You use K. You see that? If only one gas molecule, you use K. If 1 mole of gas, you use R. Okay, you use R. Okay. So now, what if the question asks for total kinetic energy of gas? We know that gas, it has many molecules. Many molecules. We don't know how many moles of it. We don't know how many moles of gas. We don't know how many total number of molecules. We can just say that this gas has n molecules. N is the total number of molecules in the gas. Or maybe the gas has n moles of gas. N moles of gas. So how to find the total kinetic energy for this gas? How? Start with half kT. Okay. See, this gas is what kind of gas? Monoatomic or diatomic or polyatomic? So just multiply the degree of freedom, 356, and then multiply by the total number of molecules. If one mole, you multiply Avogadro constant. If total molecules n, you multiply n. Then you get the total kinetic energy for this gas. Okay, multiply n. So after you multiply, you get this F over 2 nkt. Familiar with this nkt? Familiar with this nkt? This nkt, what is this nkt? What is this nkt? Nkt is PV equal to nkt. So remember PV equal to nkt? And PV also equal to nRT. Equal to nRT. And PV also equal to 1 over 3 nmv square. And nkt also PV. So the total kinetic energy of gas is F over 2 nkt. That's the formula. And this nkt, you can change. Sorry. And this nkt, you can change to nRT because nkt can change to nRT or also can change to PV. You see that? nkt can change to nRT, can also change to PV. Can also change to 1 over 3 and mv square. So if this one, I also can write F over 2 multiply 1 over 3 and mv square. This one, yeah? This formula. Okay? If let's say the question have pressure, have volume, pressure and volume, degree of freedom, and ask for total kinetic energy of gas, I also can use F over 2 PV to find the total kinetic energy of gas. Not necessarily must use the temperature. Then, because nkt is equal to nRT and also equal to PV. So when do we use big N? When do we use small n? We use nkt. Remember, we use nkt if the question gives you the total number of molecules n. We use nRT if the question gives you the number of moles, of gas. Then we just use nRT. If the question don't give you the temperature, don't give you the number of molecules, but give you the pressure and volume, you just use F over 2 pressure times volume. F over 2 pressure times volume to get the total kinetic energy of gas. If the question gives you this one, root mean square velocity, nm, we also can find the total kinetic energy of gas using this one. Understand? Good. Now, yeah. One very important thing, all this formula, F over 2 kT, 3 over 2 kT, F over 2 RT, F over 2 nkt and RT, all this T here, you must use Kelvin. Remember, this chapter always use absolute temperature, the Kelvin. Yeah? If the question gives you degree Celsius, you must change all to Kelvin. Yeah? This temperature all just change to Kelvin. Okay? Because these all are single temperature only, single temperature point. Understand? Good. Yeah? All use Kelvin. Now the next one. Now finally, what is internal energy? Internal energy is the sum of the total mean kinetic energy and total potential energy of all the gas molecules. Excuse me. Okay, so normally we talk about what? We talk about the internal energy and the internal energy of the gas. What is the internal energy of the gas? Yeah, internal energy of the gas. What is it? Yeah, what is the internal energy of gas? It's the sum of total kinetic energy and total potential energy of all the gas molecules. So the gas molecules, we learned already. the gas molecules possess what kind of energy? Okay, the gas molecule is moving around. The gas molecule is moving around, rotating around as they move around. So it has kinetic energy, isn't it? Translational, rotational, kinetic energy. It has kinetic energy, and also it has potential energy. Actually, it has potential energy. Yeah, because why? Because between the particle, yeah, the particle 1 and particle 2, these two are gas molecule. Let's say two gas molecule. Although they are far apart, but they have in between them they have intermolecular forces. Yeah, but they are negligible. Negligible because they are very far apart. They're very far apart. They are so they are very far apart. So for gases, the intermolecular forces in between the gas molecules are negligible. And potential energy depend on the intermolecular forces between the two particles. Yeah, potential energy depend on the intermolecular forces in between the gas particle. Yeah. But the intermolecular forces between the gas particle are negligible. So we can say the potential energy of the gas also negligible. So it's just like this. This is the internal energy of gas. Is the potential energy of gas plus the kinetic energy of gas. But the potential energy is zero because of negligible intermolecular forces in between the gas particle. So the internal energy of gas is solely the total kinetic energy of gas, which is also the one we learned just now. The total kinetic energy of gas we already got is half F over 2 NKT, F over 2 nRT, or F over 2 PV. We already got this total kinetic energy of gas. So this total kinetic energy of gas is, what is it? What is this? This is the internal energy of gas. The internal energy of gas. Yeah, internal energy of gas. And this is the internal energy of gas. Okay, good. So the internal energy of gas is the total kinetic energy of gas. So if the question asks for internal energy of gas, you just find the total kinetic energy of gas. Just find the total kinetic energy of gas. Use either of these three formula. Just use. Yeah. So internal energy of gas is also F over 2 NKT, the formula just now, or F over 2 nRT, or F over 2 PV. The question gives you the total number of molecules, you just use NKT. If the question gives you number of moles, you just use nRT. If don't give you either one, you just use pressure volume. Okay? So that's internal energy of gas. It is the total kinetic energy of gas. Potential energy is assumed to be zero. Right? Now, look at this formula again. So this internal energy depends on temperature. Okay? So the higher the temperature, the higher the internal energy of gas. That means the higher the temperature, the higher the kinetic energy of gas, because they are traveling faster. You look at this formula, Vrms equal to the root mean square speed. Yeah, the average speed of the gas molecules, which is square root 3 kT over m. You increase the temperature. If you increase the temperature, the gas molecule all travel faster. As they travel faster, they have higher kinetic energy. Because why? Because kinetic energy is half mv square, isn't it? So you increase the temperature, you increase all the gas molecule travel faster, higher velocity. So higher velocity, half mv square, higher velocity, higher kinetic energy. So higher kinetic energy, higher temperature, higher kinetic energy, the higher the internal energy of gas. The higher the internal energy of gas. You see that? So the root mean square speed or average speed of gas is proportional to the square root temperature. The higher temperature, the higher the velocity. The higher the temperature, the higher the internal energy of gas. Okay. So you increase the temperature, the gas molecule will start to move faster. As they move faster, they will possess higher kinetic energy. Higher kinetic energy means higher internal energy of gas. And also another thing, you need to look at this formula. VR minus equal to square root 3 kT over m. The big, you see, the bigger the mass, if the gas particle has bigger mass, it travels slower because they're inversely proportional. The bigger the mass, bigger gas molecule travel slower speed. Smaller gas particle, smaller mass travel faster. Okay, because they are inversely proportional. The bigger the mass of gas molecule, the bigger the mass, the slower it travel. The bigger mass travels slower, the smaller mass travel faster. Because speed inversely proportional with the mass. And the last thing is all this, the temperature, the VRMS, the temperature here, NKT and RT, all this temperature must change to Kelvin. Yeah, must change to Kelvin, the single temperature. All right, must change to Kelvin. Cannot use degrees Celsius. All right, I think that's it for for this chapter. So I hope you understand. If you don't understand, please leave a comment below. If you like the videos, please share it to your friends, share to more people. Please subscribe my channel. Yeah, I hope that I can continue and I will finish. Hopefully until Sem 2, I will finish all the videos. I will complete my videos up to all the semester 2 syllabus. Alright, so please subscribe my channel. Thank you very much. See you. Bye.